Okay, here in example 5, we're again going to use our exponential growth model. A is equal to A0 e to the kt. And in letter A, we're going to be asked to find the exponential growth function that models the data, which essentially means that we're going to have to find the value for k. So it says that in 1970, the population of Mexico City was 9.4 million. That sounds like an initial population, and so I'm going to call that my A sub 0, and I'm just going to put 9.4. You could put 9.4 and then a bunch of zeros, or you could just put 9.4 and then remember that everything is going to be in terms of millions of people. By 1990, it had grown to be 20.2 million, so that's actually pretty fast growth. The final amount is going to be 20.2. How long did it take to go from 9.4 to 20.2? Well, from 1970 until 1990, that is 20 years. And so I'm going to put 20 as my time, and so therefore we are looking for the value of k. And so plugging into my equation, I'm going to have 20.2 is equal to 9.4 e to the 20k, and then we're just going to go about solving for k. And so the first thing I want to do is divide both sides by 9.4. And when you do that, I would highly recommend leaving it as a fraction or using the calculator to convert back to a fraction. And so what you're going to get is 101 divided by 47 is equal to e to the 20k. Take the natural log of both sides. So the natural log of 101 divided by 47 is equal to 20k, and then divide both sides by 20 in order to get your k value. And so k is going to equal to, just plugging that into the calculator really quickly, natural log of 101 divided by 47, and then close your parentheses and divide by 20, and you're going to get 0.0382. And just as always, we're going to store that value in A. And so here is what our population model is going to look like. A is equal to my initial value, 9.4, e to the 0.0382 multiplied by t. And so with this formula, we're going to be able to plug in any value of t in order to get the population at that time, or we're going to be able to plug in any population and figure out how long it took to get to be that particular population. Now, part B is pretty straightforward. All we're going to do is pull a number off of our exponential growth function in order to answer it. It says, by what percentage is Mexico City growing? Well, I know that the rate is 0.0382, and so to move that to be a percentage, I'm just going to move the decimal place over 2 places to the right, and that's going to give me 3.82%. Okay, I've gone ahead and copied over the equation from part A so that we can answer this question. By what year will the population reach 40 million? And so I know that I'm going to look for little t, and that 40 million is going to be my A. But I'm not going to put in 40 million because I remember that this is already in terms of millions, and so I'm just going to substitute in 40. And then my objective is to solve for lowercase t. So the first thing I'm going to do, as always, is isolate that exponential expression, and converting back to a fraction is going to give you 200 divided by 47 is equal to e to the 0.0382 t. Next thing we want to do is get rid of the e, so I'm going to take the natural log of both sides. So natural log of 200 divided by 47 will equal to 0.0382 t. And then to get t by itself, we're just going to divide by that k value, which remember we have stored in our calculator. And so we're going to recall that stored value, and we're going to end up with an answer of 37.86. But that is not a sufficient answer, because we want to know in what year this is going to happen. So remember that our initial year was 1970, and so to figure out what year it is now, we're going to have to add our answer to 1970, and what you're going to end up with is 2007.86. And so the answer to this question is sometime between 2007 or 2008, that's when the population of Mexico City will reach 40 million. Okay, in this last example, we're going to look at two financial models and solve questions involving them. And so we've got this formula here. I'm going to explain what all of these variables mean, and then we'll go into solving the question. And so here, A is going to, again, represent your final amount of money. And then capital P is what we call the principal amount, but it is also just known as the initial amount of your investment or your deposit into a bank account. The R is the rate, and of course that has to be represented as a decimal. And so this 9% that we are given in this particular problem, we are going to just go ahead and automatically convert that to a decimal, 0.09. And so just make sure that you do that on every problem, otherwise you're going to get some really goofy answers. T is your time. And for this particular problem, there's also this N. And N represents the number of times that interest compounds in a year. And so just different, let me see here, it compounds in a year, and different accounts are going to have different numbers of times that interest compounds in a year. So for example, you might have an account that compounds interest monthly. In that case, N is equal to 12. You might have one that only accumulates interest once per year. You might have one that is weekly, and weekly would be 52, since there are 52 weeks in a year. Another common one is you might have an account that compounds interest quarterly, and so that would be N is equal to 4. Daily would be 365, so I'll go ahead and write that one down as well, just in case you see that one on occasion. And so this N just represents, again, the number of times that interest compounds per year. And so using this formula and plugging in what we know, we are told that the amount invested is $25,000, and so that's going to go where my P is located. The number of corresponding periods is monthly, so that means that N is going to equal to 12. We already know that our interest rate is 0.09, and the amount accumulated is $500,000. And so that's my final amount, $500,000 equals to $25,000. 1 plus my rate divided by N raised to the N T. And so now our objective is to solve for T. And so what I'm going to do first is divide by my P value onto both sides of the equation, and that's going to give me 20 is equal to 1.0075 raised to the 12t. And now I'm going to take the natural log of both sides. I'm not going to be able to cancel this 1.0075 because it's not an e. And so this is going to be a little different than the equations we've gotten used to solving in the last few examples, because that's not going to cancel out like it normally does. And so I'm going to have to use the power rule in order to move this 12t into the front. And so I'm going to do that down here. I'm going to have natural log of 20 is equal to 12t multiplied by the natural log of 1.0075. And so now, 12t. And so now in order to get t by itself, we're going to have to divide by everything that is not t. And so we're going to have to divide by 12. We're going to have to divide by the natural log of 1.0075, and that will get us t by itself. And so dividing this by 12 and the natural log of 1.0075, and then dividing this side by 12, natural log of 1.0075, we're going to get a value for t of 33.41 years. Okay, in the last problem, we're going to use a similar financial model. A is equal to PE to the RT, and you're going to know to use this formula whenever the interest is compounded continuously. So like on the previous problem, it said that the interest was compounded monthly, or you could hear quarterly, or yearly, or daily. But if you hear that interest is being compounded continuously, that's when you're going to use this formula. And so the amount invested, that's going to be my P. It's going to be 5,000. My interest rate is going to be 0.0375 as a decimal. My amount accumulated is going to double. So that means that my A is going to equal to double of 5,000, which is going to be 10,000. And we are looking for the time in years. And so using this formula, we're going to have 10,000 is equal to 5,000 e to the 0.0375 t, and we're just going to go about solving this equation for t. And so what we're going to do first, as always, is isolate that exponential expression by dividing by 5,000, and that's going to give me 2 is equal to e to the 0.0375 t. And now when I take the natural log of both sides, this is a little easier because natural log of e is going to cancel. And so I'm just going to have 0.0375 t, and to get t by itself, we'll just divide by 0.0375 so that we get a final answer of 18.48 years. Okay, that'll do it for section 3.5 and exponential equations. If you guys have any questions at all, please do not hesitate to reach out.